Okay, this week, talking about potential and capacitance. Now, just to start talking about potential, we want to know if we got to charge little q to charge big Q here, how much energy it takes to assemble that system. Okay. In other words, let's say we got charged little q here and we bring charge big Q in from a very remote place. Let's say from infinity, which is the limit of remoteness. Okay. Okay, so force between these two charges at any distance reasons we'll see in a minute. Okay, is K big Q, little q, big Q over R. And that's the magnitude of the force. It's a repulsive force if these are unlike or like charges. Attractive force if they're unlike. Okay, now work by field of Q as Q moves from infinity to R is the integral from infinity to R of negative K times little q big Q over R. Use little R here to indicate the force at any position along the R axis. I'm just integrating along some the axis defined by these 2 points. This electric force being a conservative force, you have motor variable calculus, you know that the integral of that force between any 2 points, the line integral, is going to be independent of the path between those points. So I'm simply going to choose a path along this line. I'm going to come in from infinity along the R axis. Okay. In this case, it's actually, I don't want to get into declaring unit vectors here, but your force is in this direction if these two are positive, and your displacement is in this direction. So the work done by that force is negative, because you're coming in a direction opposite the force. Now, if you happen to have unlike charges, well, it's still going to work. Okay. Okay, well, this integral then is very simple. It's going to be the negative of negative A little q big Q over evaluated in R, well, and infinity, or between infinity and R case, which is going to be this. And sign on it for some odd reason. This force is going to be opposite to that direction. You get a negative here, you get a positive here. Oh yeah, it's work done by the field. Okay? That's negative K, little q, big Q over R squared, over R. This is work done by the field. Down to symbol is it's this. Now, done per unit of approaching charge Q is KQ over R. This is potential energy per unit of charge at point P at distance R from Q. Remember, potential energies equal and opposite to the work done by the net force. So this is work done by the net force, right? And this is the potential energy, which is possible. Potential energy is the work you have to do, push the thing in, which is opposite to the work done by the net force. Okay? And the signs can be confusing. I mean, you saw me. That's relatively rigorous. Little things about the notation could be better, but you should understand this. And I think that is in the transition problem. That, yeah, I think it is. Won't say 100%. Okay, so you have this picture. You have a charge Q. Matter of fact, let's mean this. You have a little charge Q. You have some radius here. Now I'm on a flat board, so I can't draw a sphere, but right there's a circle. Every point's at the same distance. The KQ over R is the same everywhere. And then if I make this into a sphere, there, it's a nice sphere. Okay. That sphere is what we call an equal potential surface. And PE per unit charge is potential. That's what we mean by potential. What are the units? Well, this is potential energy, right? It's in joules. This is in, oh, this is charge, it's in coulombs. So this is in joules per coulomb. And what are joules? What's a joule per coulomb? If this isn't deeply embedded in your brain after having worked for a couple of months on the transition problems, you're missing something important. That's a volt. And if that doesn't ring a bell as soon as you hear a joule per coulomb, then you need to work on your bells. Okay? Because you've got a test. By a week from today. Okay, makes sense? That's potential. Which is. Okay, it's an integral of force per coulomb over a path. That ought to ring a bell, and that ought to bring a few things together. Once you understand that, the mathematics is, it's not trivial. You know, we did some last time, you know, a dipole. Okay, I think I might have made a mistake of one of those two. So let's take another quick look at it. When you try to figure out the potential of a dipole, you find that it depends on which direction you are relative to the axis of the dipole. Okay. So let's just jump directly from this, which is fundamental, which you theoretically should understand very well at this point. Okay. And you're going to need to understand it really well by the final. You're going to need to understand it pretty well, although I don't know that I'm going to have you do the integral. I don't know that I'm not. Remember, I looked at a lot of problems and just chose a bunch of good ones. Okay. And if I saw this problem, I probably included it, but I'm not sure I saw it. Anyhow. So let's just take a quick look at. Your book does use D, but I'm splitting it into an A and an A. So you probably conclude that B equals 2A or A equals D over 2. Okay? I prefer to work in terms of A, so I don't have to have the fraction. And you probably prefer that too. Okay, so if I'm at a point here, here's Y. I'm at 0Y, and this charge is going to be negative Q, and this charge is going to be Q. So we can easily write down the potential. It's K cubed over the square root of y squared plus a squared. Okay. Minus k cubed over the square root of y squared plus a squared. That's because by the Pythagorean theorem, that should be just obvious and natural. And what's that add up to? That adds up to 0. Why should that be? If you come in along the y-axis from infinity, this charge exerts a force in this direction, and this charge exerts a force in this direction. Y components of those forces are equal and opposite, right? Which leaves a force perpendicular to the y-axis. So if you're, let's say, just extend the y-axis, let's say you're up here, then you're going to have a force for this charge, and a force away from this charge. Put these together, draw them a little bigger, angle a little bit, and you can replace the two forces by their components. Right? The x components are identical, and they reinforce. The y components are equal and opposite. And what you get is just this, which is this plus this. Okay. Well, you're approaching along the y-axis so that the work done against this force is 0 because this force is perpendicular to your motion. The approach is along the y-axis. You know, I'm missing just a little bit of the board here. I think conjecture what was there. But anyhow, here it is. Here it is in terms of just potential function. But you can confirm this by the fact that the symmetry of the situation, or the little bit of asymmetry, indicates that the force is always perpendicular to your motion. If you're in this direction, now if you wiggle in and spiral in and everything, you'll finally end up here from infinity. The field is conservative, so you get the same result. Okay, that's something to get used to as you're going to be seeing it in monoverbal calculus by next week, if not before. Okay, and also, if you've had monoverbal calculus, well, there it is. Make sure you understand what a conservative field is. Really important. Okay? Make sense? Now, at the dipole field, as you approach along the x-axis, you always do have a force. Because if you're at a point of the x-axis, the magnitude of the force you get from the closer charge exceeds the magnitude of the opposite force you get from the negative charge. So that it's not quite that simple. So if at a point of the x-axis, so this point will be zero. Zero, the force is where the potential is. K cubed over x minus a minus k cubed over x plus a. Now we did the algebra this last, excuse me, and I screwed this one up. I've got the wrong expression here. So I've got a question. Let me pause for a second. See if I enlighten one of us, myself or whoever's at. Okay, remember what potential is. Again, we talk about the work done by the field to get from infinity. Okay, this charge is here. This charge is going to move in from infinity or from some large distance that's practically, okay, where it experiences a negligible force over any distance. Be understood. So we calculate the work done by the field as we move from infinity to this point. Okay. And the field does negative work if these charges have like sign. In other words, the QQ's positive. Okay. And that's because then in that case, the force is in that direction, displacement's in this direction, the work is negative. Displacement opposite direction of the force. Okay, then the work to assemble is equal and opposite to that, because that's like the work we have to do to push them together, assuming they're of like sign. So there it is. That's the work it takes to assemble this. Period. Okay. Now, we're going to regard this as a test charge. Just whatever charge we want to bring in. Okay. If there's no charge there, then at this point, we can still have a quantity, which is the amount of work it would take per unit charge to get them, to get one. Okay. So we take work per unit of approaching charge. That's a property of this point in space. It doesn't care what charge you bring in. Okay. It's just a quantity that you then multiply by whatever charge you want to bring in to get the potential energy between you and the potential energy of the system. Okay. So that's why we say this is a potential energy per unit charge at this point. It's a property of just this charge and whatever the point is. Okay. And if the point is a distance r, then you have the same result everywhere on that sphere surrounding this charge. Okay. And that's an equal potential surface for this particular charge. Okay. And it has units of what? This has units of work. This will have units, SI units, be joules. Okay. And of course, this has SI units of joules. And this has SI units of joules. But now this has units of coulombs, so this has units of joules per coulomb, which, you know, are volts. Okay. So you want to put all that together. So that's worth repeating, because that's really the fundamental idea behind potential. Potential of due to one charge at one flare. And then if we have multiple charges, if we have 5 charges, well, we get the potential for each one at that point and add them up, which is what we're doing here. We don't have 5, we've only got 2. But we add the potential due to this charge here, the potential due to this charge here. They're of opposite sign because the charges are negative, are of opposite signs. I could say, if we want to make this really explicit, just to be really careful. Okay. The distance is the same, there's a symmetry here. And the distance is explicitly square root of y squared plus a squared. Okay. The charges are opposite, so we're going to have a k cubed and a k times minus q. And it's obvious then that these two add up to 0. Then again, we talked about y approaching along the y-axis. By the symmetry of this thing, the forces are going to look like this at any point. So these components will cancel, these components will add up. Net force is perpendicular to your direction of approach. So there's 0 work done. Okay. And I'll repeat again, if you come in over some other path, yeah, over segments of that path, you could have positive or negative work, but they all cancel out. All the positives cancel the negatives. Okay. And that's due to a theorem of multivariable calculus. The conservative vector field, which is one that's a gradient of a potential, which we're going to get to here shortly, okay, is, so the integral of that field is nothing dependent. So that you just talk about the potential. It's pretty neat. It's really one of the neatest experience. It's one of the neatest theorems, if I can call it the right thing, in the universe. Okay. It's really cool. Okay. If you have a taste for something. Now, yeah, I was about to just recapitulate what I did last time. Got a point on the x-axis, then your potential is this. The only difference being this charge is positive and it's closer to this point. Its distance is x minus a. Then this charge, which is negative, it could be plus k times negative q as it was up there. Throw the negative out here. And this charge is a little further. It's an x plus a. Minus a minus 1 over x plus a. Which is k cubed times x plus a minus a quantity x minus a over x minus a, that's x plus a, which equals there's this trick that I just invented after 53 years of doing this, where I pull the board out here so I can write low. Okay, I'm a fast learner. I'm more proud of this than anything I've done within the last decade. Okay. And if you've been watching me for the last decade, you'd believe that. Okay, here we go. Okay, so it's k cubed times what? Well, your x is subtract off your age and force. You have 2a over x squared minus a squared. And you can go a little ways further with this. And see how the potential falls off. Okay, if you're coming in at some angle, one of the big things we want to talk about is dipole moment and the energy or the potential due to dipole. If you're approaching along some other line, and this picture's going to get confused, but I don't usually put color. A little bit's all I've got. Gotta find the chalk. Let's say that you're out here. At some point, I'm going to switch to polar coordinates simply because theta is a big deal. Okay. So now what I have is, well, what's my distance from here to here? What's my distance from here to? I'm not going to work all this out because it's a little involved. Okay. Take the line from here to here. Well, I know I'm going to have, well, I've got this distance. Okay. And this distance is don't really have room to write it out. If I put my x0 label over here a little bit, maybe I can. So I'm going to label my x0 here. Okay, now this is not super complicated. You've got a right triangle here. And this distance, don't want to write square roots and that stuff. Distance squared is what? It's r squared sine squared theta. Because of course, your r sine theta is your y coordinate, right? And this thing's on the x-axis. So, you know, this leg of your triangle from over here is this. This. Okay. Now I'm using theta because the final result depends on theta. So I'm just using theta from the beginning. Now you could write out the same expression for this distance. Okay. And it all goes into something that looks like this. It's just that your denominator is going to be square root of this, one of the terms on the first term, in the square root of whatever you get here. And whatever you get here is the same as what you get here, except you're going to have a plus. Does that make sense? I'm saying it kind of fast. You haven't digested it. So if you need to digest it, go back and look 22 minutes and 14 seconds into the video when I'm talking about this, and you can hear what I said. And if AIM gets good enough to actually represent my speech, and it's getting pretty close. When they first started using AI, it was terrible. Before they were using AI, it was pretty good. Then it got terrible, but now it's getting, I think, pretty good. You can look at the transcript of what I've said. Most of my words are okay, but sometimes there's a bizarre, due to my voice, or maybe I didn't pronounce something correctly. Or maybe just due to AI's shortcomings. Okay, enough of that. You understand we could do it this angle. And there's an expression, just a simple dot product. Okay. That tells you what potential would be out there. In one part of the dot product, it's just Q times the vector from here to here. Okay, in this case, it would be QI, because the I vector would be along the x-axis. Okay, and then the other vector, not surprisingly, goes from here to here. But maybe we'll make it into a unit vector, maybe we don't. maybe we divide by the distance. Okay. So we see that. Hopefully we see that in 2 months. Maybe I was done before I started it. Okay, let me pause a minute. Decide what I want to do next, because what I do depends on what I think you're understanding. Okay, now this is pretty simple. Okay, except for the order of the substrate. Okay. So it's like we have point A. We have an electric field. So we have some field. Some electric field. Okay. We follow a path from A to B. I drew a pretty complicated path. I could have drawn a straight line path. I could have drawn a path that spirals in. Okay. I could have drawn any kind of a path as long as it's continuous, no breaks. And the integral of the field over this path is going to be exactly the same thing if this is an electric field, because electric fields are always conservative. Okay. I think your book uses delta V. Del V. I often use splice of E, but that can be confused with the flux. Pi is a pretty standard notation for a potential function. Okay. But I'll just say delta V. E equals del V. I said delta V, it's del V. Okay. The del operator, as everybody should know by this point, because I think the last assignment in this semester's mononomial calculus had to do with gradients. So just a gradient of V. And I don't want to write out all the del with respect to, so I'm simply going to abbreviate the notation Vx, meaning the partial derivative of V with respect to x. Decided to write it more compactly. I'll write the whole thing. Okay. Now let me ask, why does this make sense? Okay, here's point A, here's point B. Some electric field. E of X. Well, if you integrate let me back up. Let's say you have some force here. F of X will be electric field acting at some charge Q. Now there's you got a wire here, and you got some electric field between here and here. Okay. How do you get the potential difference? Well, from the transition problems, it should be very clear that you just multiply the electric field by the distance. And we've done that in lab with wires and stuff. Okay, resistance wires. Okay. If this isn't a conducting wire, if somehow you have a variable electric field, like you've got some charged object out here and some other charged object up here that's creating an electric field between these points. Now dx with an arrow. Okay, so if you're moving along the x-axis, just I dx. That's the work done. Okay, does that make sense? Just integrating a force here. Okay, then remember that this f of x is just an electric field acting on some charge. It's just this. Now what I'm trying to invoke, what I'm trying to note here is that B is the integral of your force over Q. Then the derivative of B is the force over Q. Because the integral is an antiderivative, right? Well, this just does your dV dx and dV dy and dV dz. This takes it into 3 dimensions for the same reason that if you get your voltage function by integration over x, then the electric field, which is your force over Q, is just your dV dx. So when you go into 3 dimensions, you just combine your partial v with respect to x, your partial v with respect to y, your partial v with respect to z into your electric field. Right? It's a bit of a hand waving derivation. You know, The official prerequisites for this course don't allow me to go much further than that. Okay? But that's just a plausibility argument. You can make another plausible. Okay. Now, again, the theorem is, since E is conservative, E is a gradient field, and the integral of the gradient field is just potential here minus the potential here. It's just your potential difference, which is your VBA. Path independent. Path, now I should say any continuous path from A to B. And that's a big deal. It's a huge deal. Okay, so I'm starting to say the torque is the electric field crossed with your dipole moment, which is P. I'll put a D vector here. P is just this vector times Q. Greater dipole moment if you've got a bigger charge. But the dipole axis is what it is. Okay, so that I think your electric field is E cross P. I'm not sure about that. So let's work it out. And if your electric field is in this direction, E cross P is E cross P, P out of the board, right? Okay. Now, is that consistent? You would have a force in this direction on this charge, so you'd be pulling this one this way, and this one would be pushed this way, which means it would be rotating this way, right? And I just said the torque should be this way. So rather than memorizing which way this formula goes, just reason it out. And it can be derived easily, but just a simple consideration. If the electric field's in this direction, and you're pulling this one this way, it's going to rotate like this, which is into the board. And now P cross E is into the board. Okay. Now, the closer P is to the direction of E, the less you're going to get. If P is in the direction of E, then you get zero. Okay. Does that make sense? If you go back to what we did originally with the dipole, whatever in the world it is, it's disappeared off the face of the earth. Fields in the direction of the x-axis, you get no torque. This one is pulled this way, this one is pushed that way. Might tend to stretch the dipole a little bit, but it's not going to rotate it. Okay. If your electric field's in this direction, then it's going to tend to rotate it. If the electric field's in this direction, then this is pushed this way, this is pulled this way, it wants to rotate. So your dipole moment is here, here's your E, wants to rotate this way so that the P crossing is, yeah, that's right. So, I don't know, you think about it. I don't want to say anymore because I keep getting confused every time I pull it up my hand. But work it out. See what the book says. I seem to be contradicting myself, but I know it. Okay, so anyhow, that's one effect of the dipole. Okay. The other thing about the dipole moment is that the potential is K times P dot R squared. Now let me make sure I'm using the same notation. Yep. That's how we can easily handle. Okay, so let's think about it. What's P? Well, in this case, P is a vector in this direction, right? And let me make sure I'm recording. Yeah. Okay. D is a unit vector from the negative to the positive. Okay. In this direction. If I dot that direction with an R vector, from here out to X, then I'm taking dot product of two vectors, right? Takes the dipole moment dotted with the vector from here to here. Then if I divide that by R squared, well, sorry, if I take the dot product of this with the unit vector in this direction and then divide by the square of this distance. I get the potential difference. I get, the potential of this point relative to two. Okay. If I dot dipole moment here with a vector from here out to any point on the y-axis, I get zero, which is what the potential is on the y-axis, just by the simple symmetry argument, simple expressions we obtained first. Okay. Does that make sense? So we're talking about, again, the potential. There's a subscript in your textbook's notation. And it's just a P. So that's just potential at a point. It's potential out to finish. I wanted the potential here. Here's my R vector. And we're familiar with R vectors, right? We're familiar with making a unit vector out of our R vector. Then it's an inverse square. But the direction matters. If we're in the direction perpendicular to the dipole, dot product is going to be zero. If we're parallel to the dipole, it'll be maximized. And if it's an angle theta, then you just multiply product by cosine theta. but you get a vector. Oh, yeah, I'm sorry, you don't get a vector. Just a plot product that comes on 30 against it, and that's your potential. Yep. Whatever point P. Does all that make sense? Okay, well, I'll post the assignment this afternoon. I'll get your test into the testing center this afternoon. And get the video posted.